Right. Now, our today's topic is a se- uh, special case of, software design. This is called development before the fact technology, which based on the idea of creating safety critical system. So the person who is actually came up with these ideas or started is Margaret Hamilton. She was a software engineer, and she's the one who actually master brain behind uh, creating software systems for Apollo and Skylab, right? So let me show you a Wikipedia page, and she's the one actually coined the term software engineering, right? So let me share that. Okay, so this is the person that actually caused this type of software systems, and she was working as a director. So you can actually read about this in software engineering division in MIT. And she is the one who actually hired for building the software for NASA's Apollo program. And then she became the director. So under her directorship, they have, developed, uh, software system, which is very crucial. You know that when somebody you send it to, space, and if you make an error in your software, so you can imagine what might happen, right? And there was an image you can read about this. She was with the code that the list for the software system, and later on she got a lot of awards as well. uh, she's this is one of her official photo, NASA 1989, and she got medals. So this particular image actually getting a medal from Barack Obama for the service she had contributed to scientific and technical contributions to the domain, right? Okay, and according to the literature, and she's the one who actually coined the term software engineering, although we talk about the software design nowadays. So those days, there was no computing courses like, curriculum like ours, or there was no, courses on software engineering. But her role was pretty much critical when she's asked, develop software for Apollo, the program that is responsible for sending people to the space and getting them back. So let's get back to our the notes, especially this particular technology is called development before the fact, or in short, we say DBTF technology. And today we are going to discuss in brief what this technology is, what are the basic tools behind this, why such a technology were needed at that time, right? Okay, so let's start. Now, the technology that we are going to discuss, I told you, is called development before the fact technology. And as I told you, Margaret Hamilton is the one who actually, uh, maybe the start of use of these techniques. Because usually when we develop the software, and we try to fix the bugs later on. But usually there's a danger of when you have a safety critical systems. So what she and or her team actually that worked on is, first place, when you're designing, you try to create bug-free software. We call flawless software, because it's very important that you will not have any bugs to fix later on, which is not possible sometimes. Once you send somebody into the space, you see when there's a bug and fixing it might be a crucial, right? So the main origin of this technology is based on the software errors. Now, how this works is basically they were creating, creating visually these system models. We are going to look at like some of the examples today. And by doing so, they were able to automatically generate bug-free code. And not only the code, and as well as the document as well. Particularly like what we call 001 toolkit. And this is one of the examples they have talked about. And even this particular tool cell actually generated by itself using this technology. Now, before we go into details, first we need to know what are the problems with the existing systems, right? Now, the main issues is, when you look at our traditional way of, system engineering and software development, fixing bugs, and then before you try to fix it, you are trying to do it earlier. So the errors that we will have is especially with the software issues. So interface errors, especially what we are going to focus here. Now, when we talk about the interface errors, meaning like when you have several components of several systems, when we want to have several systems, you need to communicate, you have to exchange data, you have to interact each other. There could be a lot of issues when you have what we call the interface errors, when you have a lot of models to communicate. So this could be software modules, this could be hardware devices, or it could be a combination. So this could be for various reasons. So there could be incompatibilities, differences, communication protocols, standards, or miscommunication, or timing issues, and also like incorrect implementations, or could be problems with error handling. So the focus of the technology, what we call development before the fact, is to address these interface errors. So by doing so, they using this technology could improve the reliability and safety in software development. It's a different way of thinking, or different way of designing systems. Right, now let's look at our key principles. So the focus is in development before the fact is we need to design systems without any errors. So the focus is error prevention. And this will give you a rigorous and systematic approach. So there's a way that we need to follow. So which guarantees that you will get error-free, software system. And this actually benefited in various application and domains. So we will see like what domains in our coming slides. Right. Now, particularly when we talk about 000 tool set. So I told you like this is what Margaret Hamilton worked on. The main aim is we can look at, what are the capabilities, right? So maybe we can start by looking at so when we start looking at the idea of this is it will not useful. Then the idea that is you are not going to generate. First of all, you define what you need in a visual manner, and then you can use it to generate the code. Right. So let's look at the traditional software development issues. So the issues is mainly the fixing problems. And when we are designing, we could have done, not to create any problem. So we can say that the focus of, traditional system and engineering and software development, they focus on the problems or fixing problems, and then not to prevent them, right? So usually uh, we normally say when we get diseases in medical domain, we say prevention is better than cure. Now, similar to software engineering domain, so it's better to prevent rather than you try to fix it later on. Because when you try to fix it later on, you have to spend quite a lot of time on fixing. So it will diminish the quality of your software system and your resources are wasted. So if you can do it beforehand, then it will save a lot of time. Now, when you are going to create several components in the software systems, mainly the problem is the mismatch methods, and especially when you want to capture all your requirements, right? So when you use you have difficulties when you have like different objects, when you have different modules and different phases, you have difficulties of integrating them. So these are some of problems we will face in traditional software development. Now, when it comes to particularly problems in traditional system, we can talk about ambiguous and incorrect definitions, incompatible interfaces, and error propagations, lack of adaptability, change in user requirements and environment, and especially this is true for our old systems. And then the maintenance will be high, cost will be high, and then the development will be riskier. So these are like some of the problems. Now we are going to focus on this development before the facts technology. We focus on reusability. Now, code reusability is the term that we try to use. So when we are designing, we should focus on reusable codes, right? And also the automations, right? So our focus should be on the reusing. The problem with B is the what we have properties for these commonalities, because to reuse them you have to find commonalities so that you can use them, right? So what happens is you will get a very incomplete and efficient code generation when you're actually creating code. So there are a lot of manual processes are involved. So what we expect with this TP technology is to automate this and also trying to remove it. So now, if you look at this development before the fact, DBTF as a solution, their approach is preventive, rather than, do it like you develop and, finding errors after that. So when you're in the design stage, you focus more on, reducing that error. Oh, so this could be, look at the reusable components. So if you are focusing on preventive approach, you can address a lot of the problems that we have discussed early, and which will promote error prevention as well as efficient development. So as you can see, so this technology you can see as an alternative method of traditional development. Right. So let's start. Now, as we iterated like repetitively now, we focus of the technology is on doing these things correctly from the start. So that means in the development stage, right? So you focus on not, having errors and later on. So the focus is the preventing problems before they happen. So that means when you use the models, so you have to model both the application and its life cycle. So by doing so, you can integrate all the objects as their functionalities together. So if you can do this, that means if you can incorporate reusability, if you can reduce the errors which will happen after the development, so that means you are basically maximize the reliability and flexibility. And this will also supports the runtime performance analysis and design integrity. And since we focus on reuse, it enhances the potential for reuse, and that could be used to automate. And I told you like 001 toolkit, what they have developed is they have developed the set of tools and techniques for this, and that is also automatically generated. And that could also lead to evolution. So we can focus on quality and productivity. Right. Now, the two terms we used to use in software development, especially with the technology, is preventive as well as curative. Now, curative means our traditional way of doing this, or you fix the bugs later on. The problem with the curative approach is, what you could do is you can, if you want to accelerate the development, you can add more resources. Now, for example, when you want to add, more resources like more manpower, if you want to develop quickly, right? And also at the beginning, you focus on continuous testing. Sometimes we use like test-driven approaches where you try to eliminate error using, testing. But when you use preventive, as I told you earlier, they try to prevent errors from occurring. And how to do this? Improving the efficiency by using the reusable codes, as well as you can eliminate any unnecessary processes. So this will lead for a more reliable software system. So when you use reusing, we now talk about error-free components, right? Not the whole system. You are trying to create components which are error-free. And by creating components with reusability, we want to improve the efficiency. So when we say reuse, we talk about the software development life cycle. In the beginning of the life cycle, you use the reuse, right? So this will save time and money. So you don't have to do unnecessary development. You don't have to spend on tests and also like bug fixing, right? So that means if you reuse for, let's say, 10 successful reuses, that can save 10 unnecessary development. Right. Now let's try to understand the key ideas in this um, development before the fact technology, right? Uh, so so how do you start is we with the development before the technology, we have to define what is called properties, and then we can use that properties to control its own design and development, right? So then we can produce reusable systems, and we can also most of them automate them, right? Now when you're using the systems, we have to use what we call formal theory, right? When you are defining the systems, right? Now for that, we have to use formal system language, or we can talk about generic processes and automation. So this will be capable of defining and integrating any aspect of any system. So you can define different things, like later on we will talk about in detail, but for the time being, I can talk about, you can talk about different types, you can talk about different functions, and then later we can talk about integrating them, right? So this can lead to actually have system-oriented objects, not object-oriented systems. So we normally focus on object-oriented systems where we have objects, but we can focus on system-oriented objects. So when we talk about this, then it's semantic independent. That means the meaning-wise it's dependent, but it's syntax independent, which means you might develop using any language you want once you model it, right? So which means what we are going to use is some formal and friendly language for doing this. Right. Now let's look at how we can build such a system. So we build the model with language, and then we look at or analyze the model for correctness. Then once you do that, this part you can automatically generate so the software, especially software and also the documents, and then you can text and refine depend on what your requirement, right? So you can use this inherent testing in every development step, right? Now let's look at sometimes when you create or implement, that means you create the software as well as you will have documentation. um, it should consistent with the model that you are going to create, and then what you're going to do after you do that, you can use any language of your choice. It could be C, it could be Java or Python, and then you can actually generate this, right? So we can have a code generator, and we can configure for any new language or new architecture right in the beginning. Right. So we are going to use unique concepts. There will be axioms and some objects, and these things are applicable in the entire life cycle. Now, for example, you can have different users, you can have managers, engineers, and also end users. Then you can have, so these ideas actually came from systems theory, the formal methods, formal linguistics, and object technologies. So these are actually developed so that they can have this mismatch. We already discussed the interface errors in their Apollo space missions. So if you look back to the originating this, I told you, like, at that time, there's no systems actually develop in such a way that go through all different phases. So they worked on different research on developing software for man-rated missions, and there were a lot of interface errors. So they have come up with the theory to eliminate these errors. That's how the technology originated. Now let's look at how we could do this. Now there are, different ways of, they can talk about the theory, but when you want to build the reliable systems, we are going to talk about something called functional maps. I will explain what this is. So, as we said, it will be a recursive and reusable approach, and we are going to make use of what we call functional maps, or in short, we say F maps. So F map, if you take functional map, it's represent dynamic world of action. It can capture functional time behavior, right? Now, for example, if you take a banking system, the function could be like you make a withdraw or deposit, right? Then we have what we call type maps. There are different types, like in banking system, this could be bank manager. So type maps, usually we can represent static word of objects. Simply, it can capture the space behavior. Then we need to integrate them, right? We have to see there are some type maps and there are some functional maps. And then we are going to talk about the integration. Okay, now I think we should talk about more on functional maps and type maps. So when you talk about the function, if you take, node and its children, usually the node should control their children functions. Similarly, type maps also, you can have hierarchy, and in that case you have types. So you can have nodes controlling their children types. So there could be some operations, and then function maps, they can control the transformation, and they can make an object from one state to another. So work of functional maps can change, one state to another. And there could be some primitive types, right? It's usually at the bottom of the type maps. Right. Now let's look at this simple graphic. Now this graphic represents both functional maps. I told you this is dynamic world of actions. And then we have type maps. So you can see, this is just to give you different levels. So you can see we have some functions. These are like children functions, which can control with this, right? So we have some control structure and we have functions. And there could be some controls as well. So it can model functional behavior, and what we are using is called functional maps. Similarly, we have model type behavior with what we call type maps. So these models, then you have subtypes, right? So we can talk about the subtypes. Now, let me give you some examples. Now, I told you like these nodes. If you take one node here, for example, we have this node. So let's say this is like, function. We are going to build a table. And then there could be these are children, right? So the children could be like make parts and assemble, right? That could be a one possible, functions. Similarly, if you take like types, now since we talk about the building a table, so this could be, this could be a type table, right? And this could be the top and this could be the legs, right? So you can see the same problem. The functionalities we can, represent in F maps, and the types we can map in T maps. Right. Now that we have discussed about the F maps and T maps, we can focus more. So now we have to talk about what we call execution map. So execution map is an example of, F map, and then you will have all the object values. Similarly, you will have road maps, which organize all the objects, and that could also include both F maps and T maps. So these road maps can be generated automatically from a set of execution maps as well as type maps. So that's the idea that we are going to focus on here. Right. Now let's look at the whole design process. We get some idea about, okay, there are some functional maps, there are some type maps. So as a designer, you can start type maps first. It's a simple idea. Right now, when you say you identify different, types, right? Maybe it could be something like users, not necessarily, but you can talk about this. Okay, simple example. Let's look at some banking application since I talk about the banking application. Now, can you tell me what are the kind of types you can identify? So what are the types? Let's talk about a banking system. What are the types that we can think of when you use a banking system? Yes, Sheshan? Let's take a banking system. Let's say we are going to design. We talk about two things. We talk about the function maps, F maps, and we talk about T maps. So in T map, usually we talk about different objects, right? You can talk about object types. My question was like, what are the types you can think of in a banking system? Okay. Now the types could be something like this. Like, since we talk about the banking system, now you can think different types. Like you can think about like bank. Bank could be a one type, right? And then you will have customers or account holders. Then you can have accounts. Then the transactions, whatever deposits and the retrieval. So those are like some of the types that you can think of. Then fmaps is some functionality, right? So you can define functions and any relationships. So can you think of like some functions in relation to a banking system? Yes, what could be, if you think about the bank information system, and if you think about the function maps, like we are going to identify some functions, right? So can you give me some example for functions? Okay, now let me give some example. Now, when you look at functions related to banking system, you can talk about like a function. For example, you can have a function to create account. You can create a function for making a deposit, making a withdrawal, or even if you want to get some balance. So these are called functions. So in fmaps, function maps, you can have functional structure, right? And functional maps and the type maps usually divide the system in uh, functionally natural components. So once you identify these and the hierarchies, you can identify different functional components. So since you do this, you can see the system is integrated, and it could be understandable from the very beginning, right? So once you identify functional maps, and then uh, you know uh, type maps, right? Okay, now let's look at some primitive structures when you focus on model development. Right now we talk about two types maps, functional maps, and we talk about type maps. Now uh, you know when you want to modeling, and it's very important that we will have reliable system, right? And then we have to talk about functional and type maps. And then I told you this should be reusable. So we have to focus on recursive and reusable approach when you are designing this. Right. Now, what do you mean by primitive structures? Now, when you talk about the primitive structures, uh, when we define all the functional maps, F maps, and type maps, we have to define three control structures, right? The first one, when we talk about the parent, because in this we see parent controls like functional maps I told you, and then we have type maps. So you have parent. So parent controls is children, right? So then you have a dependent relationship. So you can have a dependent relationship, you can have independent relationship, or you can have a decision-making relationship, right? So you have to have a set of rules for each of these structures. So if you follow these, primitive structures, then you can actually avoid, or you can remove any interface errors, right? So that's what we talk about, the prevention. So if you look back our traditional development, usually we used to say that 75 to 90% of the time in traditional development you will see interface errors, right? So when you talk about the primitive structures, we define it from the very beginning, and then you are going to try to eliminate the errors from the beginning, right? Right. So let's look at this with the example. So what we are going to discuss is a small example from the textbook, uh, where we will try to understand what F maps and what T maps are. And then we look at with the example, and then we will look at the traceability of the objects. Right. Now, the first one that we are going to discuss is a maker table, where we talk about how to create a table, right? So let me show you. Let's take the picture of this to explain. So the example that I'm going to discuss is called making a table, right? So under that, we are going to have now two maps that you should know, because we discussed a couple of times, that F maps and T maps. Right, now let me share. Right, now we talk about making a table, right? We talk about making a table. So under that, we have to generate now two hierarchies. One is functions, the other one is the types. So the first one, usually we can identify the type map or T map. So if you look at very carefully about the T map, it's here. If you focus on the T map, you can have objects in this particular case, right? And then we can identify the topmost object is a table. And then you can break it down, because you can decompose this table as the top and also the legs, right? So a table may consist of a top as well as a leg. And then the top, the wood that we will actually have could be created using the hard or soft. The top could be hard or soft. Legs is, you will have number of legs. So each individual leg we can talk about here. So this will indicate the type, right? And the next one is F map, function map. So if you look at the function map, you can see here we have F map. So that means you have to have a function here. So let's say our function is make a table. And for that, you are using two types of wood. You have flat wood and round wood. right? So the next level, or the children of making a table, is you can have a function to assemble them. When you say assemble, you can assemble the top and also the legs, right? Then you can have another functionality of making a parts. You can make top as well as legs by using two types of woods in this example, flat wood or round wood, right? And then if you go down in the hierarchy, when you say make parts, that is generalized, we can talk about make top as well as make legs. So let's say that creation of the top, we use flat wood, and then to create the legs, let's say we are using round wood. Right. Okay. So now we can see the function is going two parts here. So make a parts. So you go to go down in the hierarchy. So you can create or make the top separately. Let's say plywood. So sorry, flat wood, and the leg you can use round wood. So then we can use two different tops. You can finish it with the softwood, or you can finish it with the hardwood. Right? So these are like function breakdown. So this will actually create F-map as well as T-map for this one, right? And you can see their parent-children relationship. For example, these functions, right? And the functional dependencies you can identify from here, as well as parent-child relationship we can see in the type as well. Right. Now, when you look at the type in TMAP, usually we can talk about primitive structures in children types, and we can talk about the relationships. Right. Now, we can talk about more details. Let's move on to the slides again. So what we discuss here as functional maps and type maps in the system design. So we use the example course maker table example, and we can see that you can trace all the objects because we have already defined the hierarchy here. Right. Now, if you look at this way of developing system, there are many real world applications are there, especially in real-time distributed environments can be developed using this technology. Banking, manufacturing, software development, many more could come in to use this way of this. So the important part is you can leverage out the parallelism and traceability because you know all the relationships and in the beginning itself. Right. Now, to conclude that part, we can talk about identifying these primitive structures. Especially, we can reduce the interface errors, especially when you have several modules, model incompatibilities. And we can improve the system definition and organization. And this also facilitate the reusability of the system as well as flexibility. Right. Now that we talk about the basic ideas, we should discuss, challenges as well as their limitations. So we discuss very brief idea on this, but learning curve for understanding and applying this primitive structure might take some time. And also adapting existing system to incorporate primitive structure could be challenging because remember, their focus is when you start, we are deciding. But what if already developed one, right? And the other one is how do you ensure the modeling, accurate modeling of complex systems? So those are the challenges. Right. Now that we discuss about the primitive structures earlier, so let's discuss in detail what these primitive structures are, right? So simply we talk about the parent and the child relationship or children. So we can have three, we already discussed, and then we can have a formal set of rules for each structure, and then you can eliminate interface errors, and then you can maximize error elimination, right? And the example that we have discussed, we use different functions. We have flat wood, round wood, those are the inputs, and then table will be the output. And then make a table, we can say we can decompose into parts and then assemble. So you can use, join, include, and O. So these things we have seen earlier in the example, which could be used to dependent, independent, and decision-making functions. Right. Now, when you talk about the properties of system defined with primitive structures, we can talk about the event interrupt driven. It's traceable, reconfigurable objects. You have a unique priority, and you can also identify independencies and the dependencies, and it's maximize the flexibility as well as parallelism. Right. Now that we have talked about the primitive structure, let's move on what we call defined structures. So we can say that when you talk about systems, we can use defining system with primitive structures. But the problem is we can talk about less primitive structures from the primitive ones. So we can talk about, what we call defined structures. So using defined structures, we can accelerate the process of defining and understand system. So non-primitive structures you can use for asynchronous, synchronous, and interrupt. These are different scenarios. Again, you can use for reusable pattern for functional maps as well as type maps. Right. Then let's look at how do you define non-primitive structure using primitive structures. So when you use this, we need to provide the flexibility using repeated use, ordering, and also selection of objects, right? So these rules for non-primitives, we have to get it from the primitive ones. So you can use this for asynchronous and synchronous behaviors. We can define with primitive structures, and then we can have user-defined structures, right? For example, coordinate tasks could be a system that is dependent, communicating, concurrent, synchronous, and asynchronous functions. Right. So let's look at user-defined types. Now, when you talk about reusability of type maps, we can use of different user-defined type structures. For example, one is tuple of, a set of, one of, three of. These are different structures. So again, by defining these different models, we can maximize the potential reuse of type maps. Right. Now that we have discussed about the F maps and T maps, we can talk about their interactions. Now remember, what we are trying to do here is to understand how system could be defined in a different way. In this particular case, we have to focus on reusability, avoiding any errors in the beginning, right? So as the first step, we can identify type maps and then the functional maps, and then we can talk about their integration. Right. Now, to define a complete system using this technology, we have to integrate the functional maps and type maps, right? And then we can say that the system now is ready for automatic development and also the production, right? So what happens in functional maps? You decompose until you get the primitive operations of type map types. And type maps you can decompose until you leaf nodes are primitive types or defining another type map. Right. Now let's take another example to understand this. Right. So let's say we have a manufacturing company. Let me share the give me a second to show you. I want to share another figure. Right. Right. So I hope you can see now. Right. Now, this example is you can see it as a complete system definition, and it uses a functional map, F map, as well as T map. So you can see, let's start with the T map first. So we have a manufacturing company, and then in manufacturing company, we can have department as well as employees. And then the department can management of purchasing, production, and marketing. Then we can have under the employees, we can have employee. Employee could be we can have information such as pay scale, name and skills, and the pay means the salary based on whether they actually work on full time or hourly rate, right? Now, this is, the T map. Now, when we talk about the function maps here, we will also have asked a question like, for example, we have a function called is a full-time employee, and within that you are passing employee name and manufacturing company, right? And then the answer for this is yes and no, right? And then how do you get this information is we have to go for employee manufacturing company, and then you have to find employee in a set employees, and then you have to find the particular record based on their name, and then you have to check the pay scale, right? Because pay scale, we have the information of whether they are working full-time or hourly rate. So we can look for checking pay scale. And if it is full-time, the pay scale, right? Or you can go to pay scale employee. So from the pay scale employee, you can got whether it's a full-time or an hourly rate. And finally, we can answer whether the employee is on full-time. Right. Now, this is employee time employee. It uses the objects defined by type map. So for example, here you can see manufacturing company is actually coming from here, right? And then we will got employees, employee name here, right? And then you have to, using the structure, using the name here, locating using the name, is simply we try to find the employee based on the name. And then you will go to a movie. You are going from employee. So here we will say you move employee, and then you can check pay scale employee. So you can go and check the pay. If it is full-time, then we can say yes, person is in full-time. Right. Now that we have discussed the basic idea, let's go back to the slides again. So this is just to understand how, different options available. So we have users objects defined by type map, manufacturing company, that is what we have seen. And we check whether employee is full-time or part-time. And for that, we have used locate using name structure. We use to employee based on the name. And finally, the operation, we use this to determine whether the employee is full-time. Right. Now, each what we call type structure, you can have a set of possible relations for both the parent and children types. And then we can have abstract types, the same type structure inherit the same primitive operations behavior. Now, for example, when you take manufacturing company, an employee, they inherit, primitive operations for time structure. So in this case, type structure is tuple of, which is when you have several records within that object. Right. Now, when you talk about the reuse in these operations, right? So we can use, for example, child more to child parent, you can operation of type of structure, right? So that means it's generalized. Example, when you say employees move to employees manufacturing, simply it's the same, right? It's a instance of child move to child with a parent, right? So types that could be non-primitive or primitive, or you can have a definition in another, the type subtree. Right. Let's move on to the last part. I think just to summarize what we have done so far, we look at different development strategy, especially based on reducing the errors, especially preventive way we are going to design this. So the last part, we are going to talk about what we call universal primitive operations. So these universal primitive operations we use to control objects and states inherited by all types, right? For example, you can create, destroy, copy, reference, move, access value, detect, recover errors, access the type of object, right? So these can be used to manipulate and think about different types of object. So with these universal primitive operations, we can build the system with more uniform manner. So the type maps as well as what we call function maps, we can use to facilitate and you can understand the system in a better way. Right. So T-map properties, what are the type map properties? So T-map properties ensure the proper use of objects in the functional map. So remember that in our previous example, sorry, okay, so here. So type map properties ensure proper use of objects in the F map because we have the structures, and you have seen earlier that when you are calling a function, you have to use the objects available in the type map. So this actually can control what we call spatial relationship between the objects. So you cannot change the state, and if you have any reference to the state, right? And then reject any values exist in all types for error recovery. And then if you talk about use of primitive operations, now when we have we can use rotate arm, which is a hardware system. I will show you again example of this. Let me show you the figure first. Let me share that. It should be actually rotate robot arm. So there's an error. So that's why I was wondering. So the example is called rotate robo arm. I will make the change in the note. So let me now share the figure. So in this example, what we are going to see is again use of type maps as well as what we called functional maps, right, in more advanced way. So let me share now. Right. Okay. So let's try to understand what is here. Now, in this one, what we have is you can have everything. So in this particular case, you can see software, hardware, and even the users, right? And in this particular example, we are going to define some hardware system, again using functional maps and type maps. Right. So let's start from the beginning, try to understand. Now in this one, this is called rotate robot arm. It's actually hardware system, and we are going to use to define a software system, right? And in this particular case, it uses primitives and also primitives we use for the numerical calculations. And here we have rotation of the robot arm, and it will calculate to move from one position to another in manufacturing cell to a transfer part. And the universal operation replace is, we can use this example, right? Each of these use universal operation. We use replace, and we function used to select unique, type map parent child combination, right? So let's look at the type map first. So we have robot, and then we have type tuple of, you have ports, rotation time, turn, rotate, put down time, pickup time, manufacturing object, and so on, right? And then you can also look at functional maps, where we have reset to new port, and they are assigning types from type maps, right? So here we have the other parts, ports, IO ports, a port at port. So you have a different set of ports. So IO ports, a set of IO port. It could be IO port, input output could be either input or out, right? And then you can see how the functional maps are working here. So in the here functional map, we have the function called rotate robot arm. To robot arm, you can have a 0, the object. And then you can have a set of functions. So move to starting position, end, again move to, and then here we have a calculation, compute rotation time. So this is just to show you, like, you can have both hardware as well as software in this defining in this system, right? Now let's go back again. We can talk about these expressive power and relations. Now One idea is by defining in this way, you can enhance the expressive power, right? You can talk about, sometimes a set of some structured type, and then you can talk about, for example, some object independently related to the other one. So that is one of the advantages. So this reusing is the powerful feature, as you have seen, like some of the relationship that we have defined, you can actually reuse it, right? And the idea of this technology is also we have to focus on reusability and integration this, right? And the technique that we are trying to understand here is F maps and T maps, and then we can use each of these as reusables, right? So these parts we have already done. With that, we can actually conclude the session on the topic of what we call development before the fact technology. Just to summarize, although we talk about a lot of theory, what you need to remember is, although we have everything because we have a topic on this, what you need to remember is why we talk about this development before the fact technology. I told you in the beginning, the reason is mainly when they are safety critical system, we want to reduce the errors. So usual practice is when we develop the system, we try to find bugs later. Instead of that, development before fact technology emphasize on preventing errors. Now for that, we discuss different ideas. One of the ideas that we have discussed is use of functional maps and type maps. Any system can be represented using using functional maps as well type maps. In functional map actually reuses the objects in the type maps, right? So that you are reducing the errors that can happen because you have to integrate both T maps and F maps, right? With that conclusion, let's talk about small exercise on this, right? So now that we have discussed of the ideas, let me try to, simply present you like what are the types as well as what are the functions we can discuss. Okay. So for that, I will take a whiteboard. Let me use a whiteboard here. Right. And under the whiteboard, we will look at a simple system to implement using F maps and T maps, right? So let's start looking at system. So the system that we are going to talk about in detail, especially using DBTF approach. Let's look at a banking system. Actually, this is very simplified one. We are not going to focus on everything. It will be a very complex, but just to understand, right? So let's define type map. So type map. So type map. So we call T map. So I told you like what you need to focus on in a banking system. There could be many things you can talk about, but things like bank, account holder, let's see, or a customer, account, transaction, these are like, some of the types that we could represent. And if you want, you can actually talk about, their hierarchies as well. Right now, I just want to focus only the types only. Similarly, if you want to focus on function map, or we call F map, right? There could be different function we can talk about. We can say create account. We can talk about deposit. We can talk about withdraw, right? Simple ideas. Let's talk about get balance. Now, let's look at, some integrations, right? Now, for example, now think about, let's say, remember we talk about the relationship. Now, when we have a functionality, you should use, the types when we call the function. Now, let's think about example. Let's say you are going to withdraw or you are going to deposit, right? So what are the types that you are going to access here? So what are the types you are going to access? Now let's focus on deposit and withdraw. So these are functions, right? So if you want to access deposit and withdraw, what are the types you are going to access it from here? Yes. What do you think? Now deposit and withdraw. My question was like what type you can actually use to access it. It's account, right? Yes, Kasun, it's account. Good. It could be transaction, Kasun, or in this particular case, if it is some amount, you can say amount. But what the answer I expected was account, right? So what I want to highlight is like when you are using a function, we focus on this. It should be function, right? Now, think about like drawing a T map. Can you think of drawing something? Can we think about like hierarchy of the systems what we have? Now we have already given some types, right? We said banks, we said account holder, account. This is only a part of it. Right. Now let me discuss about the details of this other one. Let's take one of the functions, at least, to understand how this is used. Right. So let's take a deposit first. So in deposit, what we can talk about here is we have, okay, we can talk about the input. Isn't it? We can talk about the input. So the type map, if you want to draw, it will be a single line. So for example, we can simply have bank. Under the bank, we can have account holder. An account holder is related to account. And then you have transactions. So let me put this way. Right. Now, in this particular case, let's check some relationship. I told you about the integration of these two. So for example, let's say withdraw deposit, let's say deposit, right? We'll have, let's say a deposit. So when you say a deposit here, deposit, now you have to, get two things, the amount and the account, right? So the input for this, let's say for this deposit, the input will be the account. So that is coming from the type map. Additionally, we have to talk about the amount that you are going to deposit, right? There is additional thing which we have not mentioned it here. And then what will be the output? So the output is like your account is updated. So the same thing account, but I will put updated account. So I will say this is updated. And then that the transaction should be recorded. Transaction. This transaction will be code. And then there are some processes also you have to think about, like when you're putting this. So first of all, you have to verify the amount, and then you have to update the account balance, and then you have to add the deposit amount. So you have to create a new transaction. So output is one of the transaction, and the type of the transaction could be a deposit, and that also you have to link into the account. Right. I think that's enough for today's session, right? I will share the chapter for you to go through and try to understand, read more on systems. And the basic idea, as I told you earlier, is this is a different way of developing and design system, such a way that you try to minimize the errors by preventing them, right? And for that, we discuss some of the key ideas of how to identify types, how to identify functions, and then how to integrate things, right? So that was the summary of today's session. So next week, what we are going to focus on, what you have already done in your previous, this is a recap. We are going to look at, object-oriented modeling tools such as user case diagrams, object modeling diagrams, as well as we can also talk about some data flow diagrams. So in the syllabus, we are supposed to recap. So please go through what we have done for your system analysis and design course. And then we will have some exercises on this. So tomorrow's session, evening, as I told you earlier, I will take it online as I'm not in the faculty this week. So I will continue our discussion on financial tools. We have discussed about first financial tool, and we are going to talk about the remaining two. I will continue. So get ready with what we have covered already so far. Already I have given you the example. Please try and come. We can discuss any issues you might have on that. Right. Thank you, guys. And then I'll stop for today.